This is section 8.5 dot product, and we'll begin by computing the dot product. And the dot product of two vectors, we'll show an example here of vector V and vector W in component form, is defined as each part of the components multiplied together and added to the next components. This result is a scalar. This is not a vector. Let's go ahead and give it a try. So given vector V and vector W in component form, let's find the dot product of the vectors. This is going to be equal to -2 times 3 plus 2 times 14. And that comes out to 22. How about the dot product of vector V and itself? We have -2 multiplied by -2 added to 2 times 2, and we come up with 8. Component form of vector W, dot product with itself is equal to 3 times 3 plus 14 times 14. Of course, you can write those as squares as well, and that would come out to be 205. Now let's talk about some of the properties of dot product. So if U, V, and W are vectors and C is a scalar, here are the properties. As you can see, that the dot product of V and W is the same as W and V. The magnitude of the dot product, the vector V dot product with itself is equal to the magnitude squared. As you can see here, if we have scalar C multiplied by a vector with the dot product of W, we can go ahead and find the dot product of vector V and W and then multiply by that scalar. The zero vector dot product with any vector is going to be equal to 0. We can distribute a vector with the dot product of the sum of two vectors. You can see here, so we can find the dot product of each one of those, and the scalar can be on the outside of the dot product with one of the vectors or with another vector. Okay, how about if we want to find the angle between two vectors? If we're given two vectors, V and W, and these are in standard position, the angle theta between our two vectors is the angle formed by the two line segments representing these vectors, where the angle is between 0 and 180 degrees. The angle between these two non-zero vectors can be given as the cosine inverse of the dot product of the vectors divided by the magnitude of each vector multiplied together. So let's go ahead and find the angle using this formula between these two vectors, V and W. So we will need the magnitudes of each vector, so we might as well go ahead and find those magnitudes now. So we have the dot product of V with itself, and we have that that's equal to, of course, -2 squared plus 3 squared, and we come up with root 13. Let's do the same for vector W, and we have that definition that magnitude is equal to the square root of the dot product of the vectors. And now we have 3 squared plus 4 squared, and we come up with 5. So the dot product of the vectors is equal to -2 times 3 plus 3 times 4, and that equals 6. With all of this, we can now find that angle. So that angle theta is going to be the inverse cosine of 6 divided by 5 root 13, and that's approximately 70.6 degrees. Okay, the cosine of theta may also be written as the dot product is equal to, and as you can see here, we just took this denominator and multiplied it by the cosine of theta. So this cosine of theta can also be written within the definition of the dot product. So if the dot product of vector v and w is positive, then the cosine of theta is positive, and theta will be between 0 and 90 degrees. If the dot product is negative, then the cosine of theta will be negative, and theta will be between 90 and 180 degrees. If the dot product is 0, then theta is going to equal 90 degrees, and we say that these vectors are orthogonal. And orthogonal vectors drawn tail to tail will form a right angle. So, to define orthogonal vectors, two vectors v and w are orthogonal if and only if their dot product is equal to 0. If these vectors are parallel, then the dot product is equal to the product of the magnitudes, or it might be the opposite of the product of the magnitudes. So let's see if these given vectors are orthogonal, parallel, or neither, okay? So let's go ahead and look at number 3. And in number 3, we can go ahead and find the dot product of vector k and s, and that's going to be 1.8 times -9 plus 0.3 times -1.5, and we'll come up with -16.65. Now, we need to go ahead and find the magnitude of vector k and the magnitude of vector s. And we learned what we can do is find the square root of the dot product of the vector with itself. So that's 1.8 squared plus 0.3 squared. And we would get approximately 0.3 or equal to 0.3 times root 37. And in the same fashion, the magnitude of vector s is -9 squared plus -1.5 squared, and we come up with 1.5 multiplied by root 37. Now we have enough information to see how these values help us to find the product of these. So I guess we could go ahead and let's move these over here, and then we will compare the product of these magnitudes to this dot product of the vectors. So here we will say that the product of these are equal to 0.3 root 37, times 1.5 root 37. And we come up with 16.65. So as you can see here, if these are parallel, the dot product is equal to one of these cases, the positive or the negative value of these multiplied together. So as you can see, therefore, the vectors are parallel. Okay, let's look at number 4. If we go ahead and find the dot product of B and A, you can see here that we'll have 2/3 times 15 plus negative 12 times 5/6, and we come up with 0. Therefore, these vectors are orthogonal. Okay, and looking at number 5, we'll go ahead and find that dot product first. And that dot product is equal to negative 60. And now let's look at the magnitude of each vector. We'll use that root of the dot product with itself. And here we'll get root 61 for vector R and root 29 for vector S. Okay, let's go ahead and multiply those together. And as you can see, we have root 69 multiplied by the root 29, and that is not comparable to this, so therefore neither. Okay, so these are neither parallel nor orthogonal. Okay, we're going to learn now how to decompose vectors into two orthogonal vectors. So if V and W are two non-zero vectors, then the vector projection of V onto W is given by, and as you can see, it's going to look like this. The projection of V onto W is equal to the dot product of V and W divided by the magnitude of W squared multiplied by vector W. Now, to compose vector V into vectors V1 parallel to W and V2 orthogonal to W, we will use these two formulas. Okay? So as you can see, the projection of V onto W is our parallel vector. And V2 is orthogonal to W. Okay, so we're decomposing vector V. So let's see, in number 6, we're given vector V and vector W, and we're going to go ahead and find the projection of vector V onto 2W. Okay, well, that is going to, let's go ahead and first find this. And remember, if you can see right here, that is going to be this part of the projection, okay? And then we will multiply that by vector W. So we can have 3 times -8 plus -1 times -3 divided by -8 squared plus -3 squared. Now, why did I do that? Because that's really the square root squared. So that's going to cancel the square root out when we square that. So this is equal to -21 over 73. So now we can come over here and say that the projection of vector V on W is -21 over 73 multiplied by 8I minus 3J, and that's equal to 168 73rds I plus 63 over 73J. Okay, now let's find vectors V1 and V2 so that V1 is parallel to W and V2 is orthogonal to W. And then we'll also find V1 plus V2, which is equal to this vector. So what we have is we have vector 1, is equal to the projection of vector V on vector W, and that's equal to 168 over 73. And here's our component form. And now vector 2 is going to be equal to vector 1 minus, vector V minus vector 1. And that's equal to 3, -1 minus this projection vector. And see if I can just make this all a tad bit smaller, just because I'd like to fit it here. So we can say that this is equal to 51 over 73 and -136 over 73. So there is our vector V2. Okay, now we're going to be using vectors to compute work. So if D is the displacement vector of an object in moving the object in a straight line from point A to B under a constant force vector F, then the work done is computed by, and here you can see that we can use the projection of vector of our force vector on the displacement vector multiplied by the magnitude of the displacement, or the work done is the magnitude of the force vector multiplied by the magnitude of the displacement vector multiplied by the cosine of theta. And theta is the angle between the vectors. The work is equal to the force vector multiplied by the displacement vector. So a force of 85 newtons is applied to move an object 20 meters horizontally. So we have an 85 Newton force. If the force is directed 44 degrees upward from the horizontal, find the work done in moving the object. So our force vector is 85. Our direction vector is 20I, since that is horizontal. And theta is equal to 44 degrees. So we have enough information to find the work using the magnitude of the force vector multiplied by the magnitude of the displacement vector multiplied by the cosine of theta. So we have 85 newtons multiplied by 20 meters multiplied by the cosine of 44 degrees. And that's approximately 1,223 Newton meters. Okay, and that concludes this section.